Okay, guys, we're going to finish up the chapter today. This chapter's been on energy. And this final topic that we're going to learn about today is called mechanical energy. So please have your chapter 7 guided notes out. There's a lot of information to fill out as we go through these slides. I'd like to start off with a definition of mechanical energy. So here it is. It is the total amount of kinetic or potential and kinetic energy in a system. So it's the total amount of potential and kinetic energy in a system. So another way of saying that is that mechanical energy is equal to potential energy plus kinetic energy. So we're just going to add them together. We're going to calculate them and we're going to add them together, and that's what's going to be our mechanical energy. Well, another way of saying this is that mechanical energy is equal to potential energy plus kinetic energy. You're supposed to write that in the notes. And then finally, let's actually go through how to calculate it. So here it is. You would calculate mechanical energy by taking mgh, because that's how we find potential energy, plus 1/2 mv squared, because that's how you calculate kinetic energy. So mechanical energy is also known as total energy. And here's why. The mechanical energy of a system does not change. The mechanical energy of a system does not change. It remains the same. So if you find mechanical energy, it's not going to change. Can we create or destroy energy, guys? There's a law called law of conservation of energy. You can't create or destroy energy. So if you find the total energy in the system, it's not going to change. It's going to stay the same. Now, can that energy go from potential to kinetic? Yeah, it can be transferred into a different form, and it can go from kinetic to potential. But the total energy of the system doesn't change. So that's going to be key to remember today. So let me give you an example of this. Let's say as the rock falls, its potential energy is turned into kinetic energy. So here's this guy. He's got this rock. At this point, all of the energy in this rock is what? Potential. Another way of showing potential, some physics textbooks will use a U. That just means potential energy. So at this point, if he's holding it here and it stops, it's got no velocity, all of that energy is potential. Now, if he drops it, some of that potential is going to be converted into what? Kinetic. And so halfway down, it's lost half of its potential energy. But notice what happened. The kinetic energy has increased. And then right before it hits the ground, all of that is now kinetic energy. So essentially what you've done is you've taken potential energy here and transferred it into all kinetic energy right before it hits the ground. The total amount of energy doesn't change. I want to emphasize that. If we put a number to this, say this was 100 joules right here of potential energy. Halfway down, now what's my potential energy? 50. Because it's lost half of its height. But kinetic energy has increased by 50. So 50 plus 50 is what, guys? 100. So if you added these together, it would still equal 100. And then right before it hits the ground, it has no height, so potential is 0. What would kinetic be at this point? It would be 100. Okay? And so the total amount of energy doesn't change, or that mechanical energy doesn't change. Pendulums are a great way to show how potential energy can be converted to kinetic energy and vice versa. So we're going to talk a lot about pendulums. It's just a weight on the end of a string here. They actually call this weight a bob. So this is a pendulum bob attached to some string, and it just swings back and forth. We know what a pendulum does. So I've labeled some points up here, P, Q, and R. Let me ask you some questions. At what point on this pendulum's path is potential energy the greatest? Potential energy. Where is it the greatest? Well, at its highest point. Its highest point is P. That's its greatest. So the potential energy right here, right before you let it go, is going to be the highest. Is there going to be any kinetic right here as you're holding it? Nope. And as it falls, it's taking that potential energy and it's turning it into what? Kinetic. So down here at point Q, now it's at the bottom of its path. It's at no height. This would be considered the floor for a pendulum. So it's all kinetic, no potential. And then as it comes back up, it's taking that kinetic and transferring it back into potential energy. Practice problem number 25. Let's see if you got this. In the pendulum shown below, which letter corresponds to the position where the potential energy is the highest? It's in your book, right? You don't have the picture, so look up here for the picture. But where is potential energy the highest? At this point. Okay, so A is where potential energy is the highest. Now let's answer the second part. Where is kinetic energy the highest? Kinetic energy is the energy of moving objects. It's going to be moving the fastest at point C. Okay. Now, before we move on, what can you say about point B? If it's halfway between C and A here, how would you relate potential energy and kinetic energy at this point? How are they related at point B? Aren't they going to be equal? Because all of it was kinetic. Halfway up, now it's going to move some of that kinetic energy over to potential energy, and halfway up, they're going to be equal. All right, it's going to be very important to understand graphs. In fact, I'm going to put a lot of graphs on the test. You've got to understand this graph right here, so let's go through it. As the pendulum bob swings, the total energy remains constant. So its mechanical energy is going to be constant. It doesn't change. While the potential energy is transferred to kinetic energy and vice versa. So let's look at this. Let's just say we start right here. You have the pendulum bob in your hand and you haven't let it go yet. So all of the energy at that point, before you let it go, is what kind of energy? Potential energy. It's all potential. This dotted line right here, this dashed line, is potential energy. So it's all potential. Is there any kinetic before you let it go? No, because its velocity is 0. So you'll notice kinetic energy, which is the solid line, is 0. Now, as you let it go and it falls down, at this point, all of its energy is what? Well, it's all kinetic now. There's no potential because it's like the floor or the ground for a pendulum. Its lowest height is right here. And then as it comes back up, now all of it again is potential energy because it's at some height. And at its highest point, how fast is it going at its highest point? Velocity would be 0. So let me point out some important things. Total energy. Does it change? So this line right here would represent mechanical energy. Is it changing? It's not. Okay. At the beginning, it's all potential. When the pendulum is at its lowest point, it's going the fastest, so it's all kinetic. It takes that kinetic energy and transfers it back into potential energy. But just notice, this mechanical energy, the total energy of the pendulum, doesn't change. Another thing, if we go back to that equation, mechanical energy is equal to potential energy plus kinetic energy. So if this is my potential and this is my kinetic, what do I get if I add them together right here? Well, you should get this right here. Let's do it again. At this point, this is potential, this is kinetic. What do I get if I was to add them together? Well, you would get this. It never changes. all of it is, at this point, kinetic. No potential. So if you add them together, obviously it's going to be right there. Okay, so I'm just trying to show you that once you know mechanical energy, it doesn't change. Okay, practice problem number 26. Let's put some numbers to this and see if we can answer them. It says the pendulum above has the mass of 2 kgs. Now this one you do have in your notes. So I want you to make these notes. The mass is equal to 2 kgs. The height from point B to point A, so this height right here is 0.2 meters. Okay, 0.2 meters. Now let's go through and I'm going to help you with this one. Part A says, which point represents the greatest potential energy? A, B, or C? Well, if we remember potential energy, it's equal to mgh. Is the mass of this thing changing? No. Is g changing? Acceleration due to gravity? No, it's not changing. Is height? Yeah, height of it's changing. Where is it going to have its highest height? Point A. And if there's no friction or air resistance, it's going to come back up to its same height. So I would say A and C. Again, that's where it's at its highest point. Part B, which point will the pendulum have the greatest kinetic energy? If you remember anything about kinetic energy, I hope that you remember it's where it's moving. It's moving energy. Where is it going to be moving the fastest? Well, at the bottom of the hill or the bottom of the swing of this pendulum. So kinetic energy is greatest at B. Okay, part C, what is the mechanical energy at point A? Well, mechanical energy we just learned is potential energy plus kinetic energy. So let's just use that equation and find its mechanical energy at point A. Well, potential energy is equal to mgh, and kinetic energy is equal to 1/2 mv squared. The mass of this pendulum was 2 kgs, so 2 times 9.8. Now how high is it at A? Well, it's 0.2 meters above its lowest point, so it's 0.2 meters. Plus 1/2, the mass is 2, times, what's its velocity at point A? 0. So all of this is times by 0, all of this goes to 0. So really all of its energy at point A is potential. So to find it, let's just times that together. 2 times 9.8 times 0.2. So the mechanical energy is 3.92. Now this is an energy value, so what are my units going to be? Joules. Yep, it's energy. We're measuring it in terms of joules. Okay, so that's the answer to part C, 3.92 joules. Guys, will that ever change no matter where you're at on its swinging motion here? So what's the mechanical energy at point B? 3.92. What's its mechanical energy going to be at point C? 3.92. Now if I stop somewhere in between, what's its mechanical energy going to be? 3.92. So that's going to be important to remember. Okay, D, let's see if you learned that. What is the mechanical energy at point B? 3.92. The mechanical energy doesn't change. Once you find its total energy, it's not like it can gain more energy. There's no such thing as just creating energy. Can't destroy it either. Okay, part E. What is the velocity of the pendulum at point C? Now think about this. You let it go at point A, it comes, it's going really fast at B, and then it comes back up to its highest point again at C. How fast is it going at its highest point? At that split second, at its highest point, how fast is it going?
0.
Yeah, the velocity right here has got to be 0. Think about it. At its highest point, it stops swinging just for a split second. So So that's going to be 0 meters per second at its highest point. Okay, part F. What is the velocity of the pendulum at point B? Now this is a good one. Okay, it actually has some velocity. We know that it's going to go, that's where it's going its fastest. How can we solve for its velocity? Well, we see velocity in one of the equations that we've studied so far in this chapter. Which one? Kinetic energy. So we know that all of the energy at point B is kinetic energy, which is equal to 1/2 mv squared. Well, what was the total energy? It's mechanical energy. We found it was 3.92, so if mechanical energy is equal to 3.92, we can set it equal, so let's do it right here. So 3.92 is equal to 1/2 mv squared. There's not going to be any potential, so I'm not going to put plus potential energy because that goes to 0 because it's at a height of 0. So 3.92 is equal to 1/2. The mass was 2, and velocity, remember, has to be squared. Now, I look at this equation, it's got one variable. We can solve for velocity. What is 1/2 of 2, guys? Isn't that 1? These 2's cancel out. So 3.92 is equal to v squared. How do you get rid of the square? Take the square root. So the velocity is equal to the square root of 3.92. 1.98. Yeah, that's what I got as well. So velocity at this point is 1.98. And what are my units for velocity? Meters per second. So that's my answer, 1.92 meters per second. Okay, I hope you were able to follow me through that and kind of think about how the energy is changing from one point to another, because that's what this whole lesson is about. Okay, let's say it wasn't a pendulum. Let's say it was a rock, okay? And let's say I drop a 1 kilogram rock or a ball from 10 meters high. Before you drop it, can you figure out the potential energy? Yeah, it's just mgh. The mass was 1, g is 9.8, height is 10, so 9.8 times 10, 98. What does that also tell us, though, guys? Before you drop it, its kinetic energy is 0. So don't we have mechanical energy? Yeah, because it's potential energy plus kinetic energy. 98 plus 0 is 98. So will this ball ever have more than 98 joules of energy? It will never have more than that. So we know that's the total energy of that ball. Halfway down, well, it's lost half of its height, so you can take its potential energy and divide it by 2. Half of 98 is 49. But it's got to have the same total energy, 98. And if you add those together, that's 98. So then we know that it must have 49 joules of potential energy. Or kinetic energy, sorry. At the bottom, right before it hits the ground, all 98 joules of energy has been turned to kinetic energy. So, knowing this, if I asked you to calculate the velocity of the ball at this point, could you do it? How would you do that? If I wanted to know the velocity here. Well, we know that kinetic energy is equal to 1/2 the mv squared. We've got the mass of the ball, it's 1. So couldn't you say that 49, because that's our kinetic energy, is equal to 1/2, the mass is 1, the velocity, we don't know, squared? Could you solve it that way? Absolutely. You could even do that right before it hits the ground and figure out how fast the ball is going right before it hits the ground. And that's kind of where we're headed. So let's move on here. Practice problem number 27. Okay, it says a 10 kilogram rock is dropped from a bridge that is 30 meters above the river below. Always, guys, I want you to draw a picture. Okay, so let's draw a picture. We got a bridge. Okay, here's the road, and here's the river below. Here's you. You're dropping this is a rock. Has the mass of 10 kgs. And the distance between your dropping point and the river below is 30 meters. Now what I would like you guys to do is try this on your own first. There's quite a few parts to this. A, B, C, D, and E. I want to give you some time to think about this on your own and answer each part, A, B, C, D, and E. If you're watching the video, please hit pause and try it on your own first. Trust me, that's how you're going to learn. Just watching me do it, you won't learn. So try it on your own. Give it an honest effort. Okay, guys, let's see how you did with this problem. I hope that you really tried it first, okay? Give it an honest effort. Now, if you have questions, that's fine. We can go over it. But you're really going to learn it a lot better if you will try it on your own first. So the problem with this slide is I don't have any space to write. So what I'm going to do is back it up. But let's answer part A first. It says, what is the potential energy of the rock before it is dropped? Okay, so let's answer that part first. So before you drop it, the potential energy is equal to mgh. So let's just plug in. The mass of the rock was 10 kgs. G is always 9.8 on Earth. And the height that it was before you dropped it, before the ground, I guess it's the river in this case, is 30 meters. Okay, so let's find out what potential energy was there. So the rock at that point has 2,940, and this is an energy value, so you report it in joules. Okay, so that's how much energy the rock had before you dropped it. It's all potential, right? Okay, part B says, what is the velocity of the rock as it hits the water below? So let's try and solve for that one. Before I do that, though, let's go back to part A. The potential energy at the very beginning is 2,940. Isn't that also going to be the total energy? Mechanical energy is equal to potential energy plus, kinetic. Sorry, that should say kinetic energy. The kinetic energy before you drop it, that goes to 0. So this value right here tells us the total energy of that rock. It will never have more than that much energy. Okay. Now let's go to B. It wanted to know what is the velocity of the rock as it hits the water below. Okay, so velocity. How are we going to solve this question? Okay, let's think about it. Well, all of the energy here before he released it was 2,940. That is going to be transferred into kinetic energy. Right before this rock hits the river below, all of that energy has now been transferred to kinetic energy. So kinetic energy at this point, right before it hits the water, is 2,940 joules. I hope that you can see that. All of the energy has been transferred to kinetic. So if we know kinetic is that, we can set that equal to 1/2. The mass of the rock was 10. And the velocity of the rock we don't know, we can solve for it. So 2,940 is equal to 1/2 times 10 times v squared. Now let's simplify it. I don't know, maybe what I would do first is take half of 10. What's half of 10? It's 5 times v squared. So I've got 2,940 is equal to 5v squared. I got to get velocity by itself. How do I get rid of the 5? Divide by 5 both sides. Over here it cancels out. So 2,940 divided by 5 is 588 is equal to v squared. Now I want to get rid of that square. How do I do it? The square root, both sides. So the square root of 588 is 24.2. And this is a velocity, so what are my units going to be? Meters per second. Okay, that's kind of cool. If we just know the total energy, we can calculate how fast it's going to be going right before it hits the water. All right, part C. It says, what is the velocity of the rock when it is halfway between the bridge and the water? So now, halfway between the bridge and the water, how high is it? 15, because down to the river was 30 meters, so halfway is going to be 15. So we want to know the velocity when it is 15 meters above the water. Now there's a couple ways you can figure this out. If we know total energy, guys, what's it going to be halfway down? It should be half. If you don't believe that, let's prove it. Okay? So let's solve for potential energy halfway down. Now the rock is how high above the water? 15 meters. Well, potential energy is equal to mgh. The mass of the rock is 10. Acceleration due to gravity is 9.8. And the height now, halfway down, would be 15. So let's solve that. 10 times 9.8 times 15 is equal to 1,470 joules. Well, how does that relate to my total energy? It's directly half. If you take 2,940 and divide it by 2, you're going to get this. So now if my potential energy at this point halfway down is equal to 1,470, where did that other energy go to? It went to kinetic, because we're transferring that total energy to kinetic energy. So we know that the kinetic energy at this point, if this is half, the other half has to be kinetic energy, so it's got to be 1,470. Okay. Well, kinetic energy is equal to 1/2 the mass times the velocity squared. So let's plug in our variables and see what we get. We know that kinetic energy was 1,470. The mass of the rock was 10. And now we're solving for the velocity, but remember, you got to square it. Okay. So again, I would do half of 10. 1/2 of 10 is 5. So let me come over here. 1470 is equal to 5v squared. Divide both sides by 5. And so v squared is equal to 294. Okay, now we got to get rid of that square. Take the square root. And so my velocity at that point halfway down, I'm getting is 17.1 meters per second. So halfway down, it's going to be going 17.1. And that logically, that makes sense because it's less than what it's going right before it hits the water. It's got to be less, obviously, so that does kind of make sense. It's not exactly half, though. How come it's not exactly half? Maybe I should ask that. If the velocity right before it hits the water is 24, if you took half that, that'd be 12.1. How come it's not 12.1? When you drop a rock, does it have constant velocity when you drop it, or does it accelerate? It's accelerating. So it's not going to be just half because the rock is getting faster and faster and faster as it falls. Okay, a couple more questions. Part D says, what is the total energy of the rock? That's easy, right? What was it? So D, the total energy is 2,940. We solved that in the very beginning. It will never have more than that. Okay, that's what it's going to have. Now part E is very important. I hope that you guys tried this one. Okay, part E says, to make a double bar graph showing the potential and kinetic energies of the rock at 30 meters, 15 meters, and 10 meters. So here's how I would do that. Here's my bar graph. I've got on the y-axis, I'm going to put energy. On this x-axis, I'm just going to put at the different points. So we have 30 meters, 15 meters when it was halfway down, and 0 meters, which right before it hit the water. Okay. Now a double bar graph for potential and kinetic. So let's just start at this 30 meters position. At the 30 meter mark, all of his energy was what? Potential. So I'm going to make a bar graph for potential, bring it up here. This is my potential energy. And what was it equal to? 2,940. Okay, 2,940 goes there. Now at the 30 meter mark, what was my kinetic? 0. So it didn't have any kinetic energy because it wasn't moving. Now let's go to the 15 meter mark. How is this graph going to look? It's going to be half and half, yeah, because now it's half the height. So the potential energy is now half. Now what's half of 2,940? 1470, yeah, so 1470 joules goes here. But if now half of it's gone, where did it go? Can I just destroy that energy? No, it was transferred to kinetic energy. So my kinetic energy is also going to be 1470. Well, what do you get if you add these together? You get the total again. Remember, this mechanical energy stays the same, always. Okay, now let's do it at 0, or right before it hit the water. What was my potential? It was 0 because it didn't have any height, and my kinetic now comes up to this 2,940 mark. It's all kinetic. Energy transformations, figuring out mechanical energy, and then being able to solve for all these different variables. This is good stuff, but this is how you solve for energy problems in physics. Okay, guys, I've got a couple more practice problems, but now we're going to go into what I call roller coaster physics. Okay, the physics of that you would see on a roller coaster. So, first of all, we have to assume something. Assume that the roller coaster does not lose energy due to friction. Now, in reality, it does. But we are going to ignore friction in our calculations. This is a little bit, well, it's not a little bit, it's a lot more complicated. So we're going to leave off friction. Okay, now I've got a couple of questions about roller coasters. Why is the first hill always the highest on a roller coaster? Why is that first hill always the highest? And this is in your notes, so we have to write something here. So here's a picture of a roller coaster. Why is this first hill, why is it always the highest? Yeah, it's trying to build up potential energy. It's trying to build up that potential energy. We get that at its highest point because potential energy is mgh. When height is the highest, it's going to be the greatest. So what I would say there is you want to start with the most potential energy, because after that, you're going to take that potential energy and transfer it to what? Kinetic energy. So you always want the first hill to be the highest. Now, what if it wasn't the highest? What if there was another hill here that came up here? Would you be able to get there on its own? No, you would have to add energy and drag it back up the hill again. And so, okay, let's describe the energy transfers that are going on with this roller coaster below. So right here it's potential. It takes up potential energy, and what does it do as it's going down the first hill? It's transferring it to kinetic energy. At the bottom of the hill is where it's going to be moving the fastest, so it's all kinetic. And there's no height here, so there's no potential. So it takes that potential energy, transfers it to kinetic. Well, then it goes back up a little hill. So what happened here? Now some of it went back into potential, but it's still moving, so it's going to have kinetic energy as well. Well, we're going to get into a lot of problems with these roller coasters. Some of the questions that you're going to be able to answer are like this one. What's the velocity of this roller coaster at the finish? And you're going to be able to solve questions like this. How fast is it going at the finish? How fast would it be going at the bottom of the hill? How fast is it going halfway down the first hill? You're going to be able to answer those types of questions. Okay, so let's get to one. Practice problem 28. It says a roller coaster above is at rest and has the mass of 200 kgs. Assume a frictionless track. Okay, and I've got a few parts to this one, A, B, and C. I would like you guys to try this on your own first. Okay, see if you can't answer A, B, and C correctly on your own. So if you're watching the video, please hit pause. Try it first. That's where you're going to learn. Okay, again, I hope you gave it an honest effort before you watch this explanation, and that you have an answer for part A, B, and C already. So here we go. Part A. It says to calculate the mechanical energy at position A. So we want the mechanical energy at point A. Well, let's go back to that definition. Mechanical energy is equal to potential energy plus kinetic energy. And it said here in the problem that the roller coaster above is at rest at point A. And it has a mass of 200 kgs. So if it's at rest right here, we know that it doesn't have any kinetic energy. So kinetic energy is going to be 0. So really, at point A, mechanical energy equals potential energy. So let's simply go ahead and find its potential energy at point A. Potential energy is equal to mgh. The mass was 200. G is always 9.8. And its height, it said here, was 30. So 200 times 9.8 times 30. So the potential energy at this point is 58,800. Okay, but that's not what part A wanted. It wanted mechanical energy. Well, we said that the mechanical energy is going to be equal to its potential energy because it wasn't moving at part A, so that's 0. So really, mechanical energy at point A is 58,800 joules. Okay. That's the answer for part A. Who got it right? Very good. Part B, let's go to that one. This one says find the potential and kinetic energy for the block at position B. Okay, so let's go to position B here and try to find, we want both potential energy and kinetic energy. Now on these problems, guys, I think the easiest place to always start is potential energy. Especially if they give us the height here, I mean, that's an easy place to start. So potential energy is equal to mgh. The mass of the roller coaster was 200 times 9.8, and it said that the height at point B was 10 meters. Okay. So see how easy that is to solve. 200 times 9.8 times 10. And so I'm getting that the potential energy is equal to 19,600 joules. So there's part of my answer for number 2 or letter B here, potential energy. Now, how do we find kinetic energy? Good. You just subtract it. If we go back to this definition of mechanical energy, it's equal to potential plus kinetic. So you just subtract it. Here's what I mean. Mechanical energy is equal to potential energy plus kinetic. Well, we've got mechanical energy. It's going to stay the same. We can't create more energy than that. It's always going to stay the same. So 58,000 800 is equal to the potential energy we just solved for is 19,600 plus the kinetic energy. So exactly, all we have to do is subtract from both sides 19,600. So let's do that. 58,800 subtract 19,600. So I'm getting that the kinetic energy is equal to 39,200 joules. Okay, and again, that's at point B. So always realize if you've got the total energy, if you've got mechanical energy, you've got a huge clue to help you solve for these questions or these problems as you go through. Anywhere on the track, this thing is always going to have 58,800 joules worth of energy. Okay, so these two numbers here have got to add up to 58,800. Okay, let's finish this one up. Part C, it says, what is the velocity of the block at point C? So now we want to know how fast it's going in part C. Well, in order to calculate velocity, what do I need to know? Where do you see velocity at in our equations that we've looked? It's in the kinetic energy. It's equal to 1/2 mv squared. So if I knew its kinetic energy here, I can easily solve for v. That's the path. That's where we want to go. So let's try and figure it out. Well, again, I think the easiest place to start is potential energy, especially when you have the height. It's equal to mgh. The mass doesn't change. It's 200 times 9.8 times the height here is 25. Okay, so let's find out what that is. So potential energy is equal to 49,000 joules. Well, that's cool, but that's not what we wanted to know. We wanted to know what kinetic energy was. But if I've got potential and I've got the mechanical energy, how can I get kinetic? Again, you just have to subtract them. So we'll take 58,800 and subtract off 49,000. And so the rest of that total energy has to be kinetic, which was 9,800 joules. I hope that you guys see that. Again, if we were to add these two numbers together, we would get the total mechanical energy. All right, now that's cool because we can use that to solve for velocity. So 9,800 is equal to 1/2. The mass of this roller coaster doesn't change, it's 200 times v squared. We want to know its velocity. So here's how I would do it. What's half of 200, guys? 100. So 9,800 is equal to 100 v squared. Want to get v by itself? Let's divide both sides by 100. Cancels out there. Isn't that 98 is equal to v squared? How do you get rid of the square here, guys? Square root, both sides. So v is equal to the square root of 98. Let's actually put a number to that. So the velocity at point C is I guess it rounds to 9.9. And we're talking about velocity, so it's meters per second. How many of you guys got that? Good job. 9.9 meters per second. I think it's amazing that we can use these energy equations and solve for how fast it's going at different points. If you were a roller coaster engineer, would that be useful information? Of course it would. Of course it would. Okay, I've got one more question for you guys. This is your last chance to go through a problem like this. So let's do it. Practice problem 29. Okay, it says a roller coaster shown in the figure above has the mass of 750 kgs. It's pulled up to point 1 where it and its screaming occupants are released from rest. So it's going 0 in terms of its velocity at point 1. Okay? What I would like you guys to do on your own this time is answer part A, B, C, and D. Again, please try it on your own. If you're watching the video, hit pause and complete this one on your own. Okay, let's see how you guys did. Hopefully, you have an answer for all A, B, C, and D at this point. So, let's go through. I'm going to explain A and B, and then I'll write down the answers for C and D, but I'm not going to explain it on the video. So let's go through part A right now. It says calculate the mechanical advantage or the mechanical energy at point 1. Okay, mechanical energy is equal to potential plus kinetic energy. So let's do that. At point 1, guys, if its velocity is 0, its kinetic energy is also 0. So at point 1, the mechanical energy is equal to potential. Do we understand that? Because if it's going 0, its kinetic energy is 0. So all we have to do is solve for potential energy, which is equal to mgh. The mass, did it tell us the mass? 750. Times g, which is 9.8. Now what's the height at point 1? Well, it called it HA. And then it gave us a value for HA over here is 40 meters. So we're going to times that by 40. 750 times 9.8 times 40. I hope that you guys got for this that the mechanical energy is equal to 294,000 joules. Okay. Again, if you times these all together, you should get 294,000. That's going to be our mechanical energy because it doesn't have kinetic right here. Okay. That's always the best place to start. Once you know mechanical energy, it's never going to change. What's its mechanical energy right here? Same thing, 294,000. What's its mechanical energy right here? 294,000. So that's a really big clue when you're figuring out these problems. Now I'm going to go and explain B, which is very similar to C and D. So let's do that one. Part B. How fast is the roller coaster going at point 2? When it says how fast, guys, what does it want us to know? It's asking us to find velocity. It's velocity at point 2. Well, at point 2, guys, does it have any height here? Or is it at the bottom of its track? Yeah, it's at the bottom of its track. Now, some of you might be thinking it does have this height. What about this height? Well, what if it never goes lower than this? Doesn't this become its floor or its ground? And that's the case. This is going to be a height of 0. Don't let this throw you off. It never goes lower, it says, than 0.2. So basically what's happening is all of the potential energy at 0.1 is being converted into what here? Kinetic energy. Because if it doesn't have a height, potential energy is 0. So what is its kinetic energy at that point? Well, if the potential energy here was 294,000, and all of it's being transferred to kinetic, the kinetic energy there is 294,000 joules. Okay, but that's not what it asked. It asked us to find how fast it's going, so a velocity. Well, this 294,000 is equal, if that is its kinetic energy, it's equal to 1/2 the mass, which is 750, times its velocity squared. So what I would do is take half of 750 right now, which is 375. So 294,000 is equal to 375 v squared. Divide both sides by 375. Okay. So 294,000 divided by 375. And I get this. 784 is equal to v squared. How do I get rid of the square? Square root. Square root of 784, so velocity is equal to 28 meters per second. And again, that's for 0.2. So this is going to be 28 meters per second. Okay, now what I would like you guys to do is C and D on your own. Okay, so please try it at this point. Okay, so I hope you went through and solved C and D. On C, guys, what did we get? 18.8 meters per second. And then at point 4, so part D, we got 22 point velocity is equal to 22.1 meter per second. Okay, so I hope that you went through and did that. Guys, before we quit, this is kind of complicated stuff. I've given you some more practice with this in the student workbook. There's a conservation of energy worksheet. I want you to do that. Okay, again, it's called Conservation of Energy Worksheet. It's actually 4 pages. So spend some time, now that you know how to do these types of problems, spend some time, get some more practice, and let's get that done, and hopefully this video helped.